Imagine a universe where time bends, space stretches, and reality itself is woven from threads of mystery. A place where black holes devour light, dark energy pushes galaxies apart, and the echoes of the Big Bang still whisper secrets from the dawn of existence. This is not science fiction, it's the cosmos as we know it, a realm of infinite wonders and unanswered questions. What lies beyond the edge of our observable universe? Are we alone in the vast expanse, or is life a cosmic inevitability? And what does it mean to exist in a universe that is both breathtakingly beautiful and profoundly indifferent? From the quantum flickers of the smallest particles to the colossal dance of galaxies, the universe challenges us to rethink everything we know about reality, time, and our place in the grand tapestry of existence. Join us on a journey to the frontiers of knowledge, where science meets philosophy and the mysteries of the cosmos unfold. This is not just a story about the universe, it's a story about us, the curious beings who dare to look up at the stars and ask, what's out there? The Big Bang and the origin of the universe. The story of our universe begins with the Big Bang, an event that occurred approximately 13.8 billion years ago. According to this theory, the universe started as a singularity, a point of infinite density and temperature. In an instant, this singularity expanded, giving birth to space, time, and all the matter and energy that would eventually form galaxies, stars, planets, and life itself. The Big Bang is not just an explosion in space, it is the expansion of space itself, a rapid stretching of the fabric of the cosmos. But what caused the Big Bang? And what, if anything, existed before it? These questions push the boundaries of our understanding. The Big Bang theory describes the evolution of the universe from a fraction of a second after its birth, but it doesn't explain what triggered this event or what might have preceded it. This has led scientists to propose several speculative theories. One such theory is the oscillating universe theory, which suggests that the universe undergoes endless cycles of expansion and contraction. In this model, the Big Bang is not a one-time event, but part of an infinite loop. After expanding for billions of years, the universe could eventually slow down, stop, and begin to collapse under its own gravity in a big crunch. This collapse would lead to another singularity, which could then explode in a new Big Bang, starting the cycle anew. It's a cosmic dance of creation and destruction, with no beginning and no end. The idea of an oscillating universe is both fascinating and controversial. On one hand, it offers a way to avoid the problem of a singular beginning, suggesting that the universe has always existed in some form. On the other hand, it raises questions about the nature of time and the laws of physics. For example, if the universe has gone through countless cycles, why do we see no evidence of previous universes? Moreover, current observations suggest that the expansion of the universe is accelerating, driven by dark energy, which makes the idea of a future contraction less likely. Despite these challenges, the oscillating universe theory remains an intriguing possibility, reminding us that our understanding of the cosmos is still evolving. Another compelling idea is the multiverse theory, which proposes that our universe is just one of many universes, each with its own physical laws and constants. Imagine a vast cosmic ocean where countless universes bubble up and disappear, each one potentially different from the others. Some universes might be similar to ours, with stars, galaxies, and planets, while others could have entirely different dimensions or forces of nature. In this multiverse, the Big Bang might not be a unique event, but rather one of countless such occurrences. The multiverse theory is rooted in several branches of modern physics, including string theory and cosmic inflation. According to inflationary cosmology, the rapid expansion of the universe in its earliest moments could have created bubbles of space-time, each one becoming a separate universe. These universes could be connected by higher dimensional structures, or they might exist entirely independently of one another. Some scientists even speculate that collisions between these universes could have triggered events like the Big Bang in our own universe. While the multiverse theory is fascinating, it is also highly speculative. One of the main challenges is that, by definition, other universes would be beyond our observable horizon, making them difficult, if not impossible, to detect. Nevertheless, the idea of a multiverse has captured the imagination of scientists and philosophers alike, offering a new perspective on the nature of reality and our place within it. Then there's the quantum fluctuation model, which suggests that the universe could have arisen from a random fluctuation in a quantum vacuum. In the quantum world, particles and antiparticles constantly pop in and out of existence, creating a bubbling soup of energy. According to this model, our universe might have started as a tiny bubble of false vacuum energy that, due to quantum effects, began to expand rapidly. This expansion would have led to the creation of matter, stars, galaxies, and eventually, life as we know it. In this scenario, what existed before the Big Bang could have been a quantum vacuum, a sea of particles and antiparticles, with our universe being just one random bubble that grew into something much larger. The quantum fluctuation model is closely tied to the concept of vacuum energy, a form of energy that exists even in empty space. According to quantum field theory, the vacuum is not truly empty, but is instead filled with fluctuating fields that can give rise to particles and energy. If a fluctuation were large enough, it could create a region of spacetime that expands rapidly, forming a new universe. This idea is supported by the principles of quantum mechanics, which allow for such random fluctuations to occur. However, the quantum fluctuation model also raises difficult questions. For example, why did this particular bubble expand while others did not? And how do we reconcile the idea of an eternal quantum vacuum with the apparent age of our universe? Despite these challenges, the model offers a compelling explanation for the origin of the universe, suggesting that it could have emerged from the chaotic and unpredictable nature of the quantum world. Another intriguing theory is the no-boundary proposal, championed by physicists Stephen Hawking and James Hartle. According to this theory, the universe did not emerge from a singularity, but instead has no boundary in time or space. Imagine the universe as a four-dimensional sphere, similar to the surface of the Earth. Just as you can travel around the Earth without falling off the edge, you can travel through the universe without encountering a boundary. In this model, the Big Bang is not a singular point, but a smooth transition, like the North Pole on a globe. Asking what happened before the Big Bang becomes as meaningless as asking what lies north of the North Pole. The no-boundary proposal is an attempt to reconcile quantum mechanics with general relativity, offering a way to describe the universe without invoking a singularity. It suggests that the universe is finite but unbounded, with no beginning or end in the traditional sense. While this theory is elegant and mathematically appealing, it is still the subject of ongoing research and debate. Nevertheless, it represents a bold attempt to push the boundaries of our understanding and explore the nature of time and space. Finally, there's the Big Bounce theory, which combines elements of the oscillating universe and quantum mechanics. According to this theory, the universe does not collapse into a singularity, but instead reaches a minimum size before bouncing back and beginning to expand again. This bounce is driven by quantum effects, which become significant at extremely small scales. In this model, the Big Bang is not the beginning of time, but rather a transition from a previous contracting phase to a new expanding one. The Big Bounce theory offers a way to avoid the singularities that plague other models, suggesting that the universe has no true beginning or end. Instead, it undergoes endless cycles of expansion and contraction, each one giving rise to a new universe. While this idea is still speculative, it is supported by some interpretations of quantum gravity, which suggest that quantum effects could prevent the universe from collapsing into a singularity. Each of these theories, oscillating universe, multiverse, quantum fluctuation, no-boundary proposal, and Big Bounce, offers a different perspective on the origin of the universe. They challenge our understanding of time, space, and existence, pushing the boundaries of human knowledge. While we may not yet have definitive answers, the search itself is a testament to the power of human curiosity and the enduring quest to understand our place in the cosmos. As we continue to explore these ideas, we inch closer to unraveling the mysteries of the universe and the nature of reality itself. The structure of the universe. The universe is not a uniform, featureless expanse. Instead, it is a vast, intricate web of galaxies, galaxy clusters, and cosmic voids, all interconnected in a structure that resembles a cosmic tapestry. This large-scale structure, often referred to as the cosmic web, is one of the most fascinating and complex features of the universe. It tells the story of how matter, under the influence of gravity and dark energy, has evolved over billions of years to form the universe we see today. At the heart of this cosmic web are galaxies, the building blocks of the universe. Galaxies come in various shapes and sizes, from spiral galaxies like our Milky Way to elliptical galaxies and irregular galaxies. Each galaxy contains billions or even trillions of stars, along with vast clouds of gas and dust. But galaxies are not scattered randomly throughout the universe. Instead, they are organized into clusters and superclusters, connected by filaments of dark matter and gas. Galaxy clusters are among the largest structures in the universe, containing hundreds or even thousands of galaxies bound together by gravity. These clusters are not isolated. They are part of even larger structures called superclusters, which can span hundreds of millions of light years. Our own galaxy, the Milky Way, is part of the Local Group, a small cluster of galaxies that includes the Andromeda Galaxy and about 50 other smaller galaxies. The Local Group, in turn, is part of the Virgo supercluster, a massive collection of galaxy clusters that stretches across 110 million light-years. But the cosmic web is not just made up of galaxies and clusters. Between these dense regions lie vast, empty spaces known as cosmic voids. These voids are regions of space where the density of matter is significantly lower than the cosmic average. Some voids are relatively small, spanning tens of millions of light-years, while others are enormous, stretching hundreds of millions of light-years across. One of the largest known voids is the Botez void, a region of space about 330 million light-years in diameter that contains only a handful of galaxies. The existence of these voids is a direct consequence of the universe's evolution. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, but tiny fluctuations in density, imprinted by quantum fluctuations during cosmic inflation, created regions that were slightly denser or less dense than their surroundings. Over billions of years, gravity amplified these differences, pulling matter into the denser regions and leaving behind the emptier voids. The result is the cosmic web we observe today, a network of filaments and nodes, with galaxies and clusters concentrated in the densest regions and vast voids in between. But what fills these voids? While they are often described as empty, they are not completely devoid of matter. Voids contain very few galaxies, but they are filled with dark matter, dark energy, and a sparse distribution of gas. In fact, the study of voids provides valuable insights into the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. Because voids are less dense, they are more sensitive to the effects of dark energy, making them ideal laboratories for testing cosmological models. The cosmic web is not static. It is constantly evolving. Galaxies and clusters move under the influence of gravity, and the filaments of the cosmic web act as highways, guiding the flow of matter. Over time, smaller structures merge to form larger ones, a process known as hierarchical structure formation. For example, the Milky Way and the Andromeda Galaxy are on a collision course and are expected to merge in about 4.5 billion years, forming a new, larger galaxy, often referred to as Milkomeda. But the cosmic web is not just a product of gravity. It is also shaped by the interplay between dark matter and dark energy. Dark matter, which makes up about 26.8% of the universe's mass-energy content, provides the gravitational scaffolding for the cosmic web. It clumps together to form halos around galaxies and clusters, while its gravitational pull draws matter into the filaments and nodes of the web. Dark energy, on the other hand, makes up about 68.3% of the universe and acts as a repulsive force, driving the accelerated expansion of the universe. This expansion stretches the cosmic web, causing galaxies and clusters to move farther apart over time. The study of the cosmic web is not just about understanding the distribution of matter in the universe. It is also about uncovering the history of the universe itself. By mapping the large-scale structure, scientists can trace the evolution of the universe from its earliest moments to the present day. For example, the distribution of galaxies and voids provides clues about the initial conditions of the universe. the nature of dark matter and dark energy, and the processes that shape the cosmos. One of the most powerful tools for studying the cosmic web is the cosmic microwave background, CMB, the afterglow of the Big Bang. The CMB provides a snapshot of the universe when it was just 380,000 years old, revealing the seeds of cosmic structure that would eventually grow into galaxies and clusters. Tiny fluctuations in the temperature of the CMB correspond to regions of slightly higher or lower density, which served as the building blocks for the cosmic web. In addition to the CMB, astronomers use large-scale surveys to map the distribution of galaxies and voids. Projects like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DS, have created detailed three-dimensional maps of the universe, revealing the intricate structure of the cosmic web. These maps not only help us understand the universe's past, but also provide insights into its future. For example, by studying the rate at which galaxies and clusters are moving apart, scientists can predict how the cosmic web will evolve over billions of years. The cosmic web is a testament to the power of gravity and the complexity of the universe. It is a dynamic, ever-changing structure that reflects the interplay between matter, and dark energy. As we continue to explore the universe, the cosmic web serves as a reminder of the vastness and beauty of the cosmos and of the countless mysteries that remain to be uncovered. In the next part of our journey, we will delve deeper into the role of dark matter and dark energy in shaping the universe, and how these mysterious components influence the evolution of the cosmic web. From the smallest particles to the largest structures, the universe is a tapestry of interconnected phenomena, each one telling a part of the story of our cosmic origins. Dark matter and dark energy. The universe is a vast and mysterious place, and much of its composition remains hidden from our direct observation. Two of the most enigmatic components of the cosmos are dark matter and dark energy. Together, they make up about 95% of the universe's total mass energy content, yet their true nature remains one of the greatest unsolved mysteries in modern physics. These invisible forces shape the universe on the largest scales, influencing the formation of galaxies, the expansion of the cosmos, and the ultimate fate of everything we know. Dark matter, the invisible scaffolding of the universe. Dark matter is a mysterious substance that does not emit, absorb, or reflect light, making it invisible to our telescopes. Despite its elusive nature, its presence is inferred through its gravitational effects on visible matter, such as stars, galaxies, and galaxy clusters. The story of dark matter begins in the 1930s, when Swiss astronomer Fritz Zwicky observed that galaxies in the Coma cluster were moving much faster than expected based on the visible matter alone. He proposed the existence of Dunkel Materie, dark matter, to explain this discrepancy. Since then, evidence for dark matter has continued to mount. One of the most compelling pieces of evidence comes from the rotation curves of galaxies. Stars on the outer edges of spiral galaxies orbit the galactic center at speeds that cannot be explained by the gravitational pull of visible matter alone. If only visible matter were present, these stars should be moving more slowly. Instead, their high speeds suggest the presence of a massive, invisible halo of dark matter surrounding the galaxy. Another key piece of evidence comes from gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. When light from a distant galaxy passes near a massive object, such as a galaxy cluster, the object's gravity bends the light, creating distorted or magnified images of the background galaxy. By studying these distortions, astronomers can map the distribution of mass in the foreground object. In many cases, the mass required to produce the observed lensing effects far exceeds the mass of visible matter, pointing to the presence of dark matter. Dark matter also plays a crucial role in the formation of the cosmic web, the large-scale structure of the universe. In the early universe, tiny fluctuations in density, imprinted by quantum fluctuations during cosmic inflation, created regions that were slightly denser or less dense than their surroundings. Dark matter, being the dominant form of matter, clumped together under the influence of gravity, forming the scaffolding for the cosmic web. Ordinary matter, made up of atoms, followed the gravitational pull of dark matter, eventually collapsing into the dense regions to form galaxies and galaxy clusters. Despite its profound influence, the true nature of dark matter remains a mystery. Scientists have proposed several candidates for dark matter particles, including weakly interacting massive particles and axions. WIMPs are hypothetical particles that interact only through gravity and the weak nuclear force, making them extremely difficult to detect. Axions, on the other hand, are extremely light particles that could explain certain anomalies in particle physics. However, despite decades of searching, no direct detection of dark matter particles has been confirmed. Dark energy, the force behind cosmic acceleration. While dark matter shapes the structure of the universe, dark energy governs its expansion. In the late 1990s, astronomers made a startling discovery. The expansion of the universe is not slowing down, as expected due to gravity, but is instead accelerating. This discovery, based on observations of distant supernovae, earned the 2011 Nobel Prize in Physics and fundamentally changed our understanding of the cosmos. Dark energy is the name given to the mysterious force driving this accelerated expansion. Unlike dark matter, which clumps together and exerts a gravitational pull, dark energy appears to be a repulsive force that acts against gravity, pushing galaxies apart. It makes up about 68% of the universe's total energy content, making it the dominant component of the cosmos. The simplest explanation for dark energy is the cosmological constant, a term introduced by Albert Einstein in his equations of general relativity. Einstein originally introduced the cosmological constant to describe a static universe, but he later abandoned the idea when Edwin Hubble discovered that the universe is expanding. However, the discovery of cosmic acceleration has revived interest in the cosmological constant, which could represent the energy density of empty space, or the vacuum energy. Another possibility is that dark energy is not constant but varies over time. This idea is embodied in theories of quintessence, a dynamic field that could change in strength and influence the rate of cosmic expansion. Unlike the cosmological constant, quintessence could interact with other forms of matter and energy, leading to a more complex evolution of the universe. The nature of dark energy has profound implications for the ultimate fate of the universe. If dark energy remains constant, as the cosmological constant suggests, the universe will continue to expand at an accelerating rate. Over time, galaxies will move farther apart, and the universe will become colder and darker, eventually leading to a state known as the Big Freeze or heat death. In this scenario, stars will burn out, galaxies will fade away, and the universe will become a vast, empty expanse. However, if dark energy evolves over time, other scenarios are possible. For example, if dark energy becomes stronger, it could lead to a big rip where the repulsive force of dark energy overcomes gravity, tearing apart galaxies, stars, and even atoms. On the other hand, if dark energy weakens, gravity could eventually regain dominance, causing the universe to collapse in a big crunch. The interplay between dark matter and dark energy. Dark matter and dark energy are often described as opposing forces. Dark matter pulls the universe together through gravity, while dark energy pushes it apart. However, their relationship is more complex. In the early universe, dark matter dominated, driving the formation of galaxies and galaxy clusters. As the universe expanded, the density of dark matter decreased, while the influence of dark energy grew. Today, dark energy is the dominant force, shaping the large-scale structure of the universe and determining its ultimate fate. The interplay between dark matter and dark energy is a key area of research in cosmology. By studying the distribution of galaxies and the rate of cosmic expansion, scientists hope to uncover the properties of these mysterious components and their role in the evolution of the universe. Projects like the Euclid Space Telescope and the Large Synoptic Survey Telescope, LSST, aim to map the distribution of dark matter and measure the effects of dark energy with unprecedented precision. The search for answers. Despite their profound influence, dark matter and dark energy remain elusive. Detecting dark matter particles requires highly sensitive experiments, such as those conducted in underground laboratories or using particle colliders. Meanwhile, understanding dark energy requires precise measurements of the universe's expansion history, often obtained through observations of supernovae, galaxy clusters, and the cosmic microwave background. The quest to unravel the mysteries of dark matter and dark energy is one of the most exciting and challenging endeavors in modern science. These invisible forces not only shape the universe on the largest scales, but also hold the key to understanding its origins, evolution, and ultimate fate. As we continue to explore the cosmos, we inch closer to uncovering the secrets of dark matter and dark energy, shedding light on the hidden fabric of the universe. In the next part of our journey, we will explore the cosmic microwave background, CMB, the afterglow of the Big Bang, and how it provides a window into the early universe. From the smallest particles to the largest structures, the universe is a tapestry of interconnected phenomena, each one telling a part of the story of our cosmic origins. The cosmic microwave background, CMB. The cosmic microwave background, CMB, is one of the most important discoveries in modern cosmology. It is the afterglow of the Big Bang, a faint radiation that permeates the entire universe and provides a snapshot of the cosmos when it was just 380,000 years old. This ancient light, first detected in 1965 by Arno Penzias and Robert Wilson, offers a unique window into the early universe, revealing the conditions that gave rise to the galaxies, stars, and planets we see today. The discovery of the CMB. The story of the CMB begins in the mid-20th century, when scientists were trying to understand the origins of the universe. According to the Big Bang theory, the universe began as a hot, dense state and has been expanding ever since. As the universe expanded, it cooled, allowing particles to form and eventually combine into atoms. About 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, a process known as recombination. Before recombination, the universe was a hot, opaque plasma of charged particles, and photons, particles of light, were constantly scattered by electrons, making the universe as dense and foggy as a thick soup. However, once neutral atoms formed, photons could travel freely through space, and the universe became transparent. These photons, released during recombination, have been traveling through the universe ever since, gradually cooling as the universe expanded. Today, they form the CMB, a faint glow of microwave radiation that fills the cosmos. The discovery of the CMB was accidental. In 1965, Penzias and Wilson, working at Bell Labs in New Jersey, were using a sensitive radio antenna to study radio waves from space. They detected a persistent background noise that seemed to come from all directions in the sky. After ruling out all possible sources of interference, they realized they had stumbled upon the afterglow of the Big Bang. This discovery provided strong evidence for the Big Bang theory and earned Penzias and Wilson the 1978 Nobel Prize in Physics. The CMB as a cosmic time capsule. The CMB is often described as a baby picture of the universe. It captures the state of the cosmos at a critical moment in its history, just as it transitioned from a hot, dense plasma to a cooler, transparent state. By studying the CMB, scientists can learn about the early universe's temperature, density, and composition, as well as the seeds of cosmic structure that would eventually grow into galaxies and galaxy clusters. One of the most striking features of the CMB is its uniformity. The temperature of the CMB is remarkably consistent across the sky, varying by only a few parts in 100,000. This uniformity supports the idea that the universe underwent a period of rapid expansion, known as cosmic inflation, shortly after the Big Bang. During inflation, the universe expanded faster than the speed of light, smoothing out any irregularities and creating the nearly uniform conditions we observe in the CMB. However, the CMB is not perfectly uniform. Tiny fluctuations in temperature, known as anisotropies, reveal the seeds of cosmic structure. These fluctuations spawn to regions of slightly higher or lower density in the early universe. Over billions of years, gravity amplified these differences, causing denser regions to collapse and form galaxies, while less dense regions became the vast cosmic voids we see today. Mapping the CMB. Since its discovery, the CMB has been studied in increasing detail by a series of ground-based and space-based observatories. One of the most important missions was the Cosmic Background Explorer, COB, launched by NASA in 1989. COBE provided the first precise measurements of the CMB's temperature and confirmed the existence of the tiny anisotropies predicted by the Big Bang theory. This work earned John Mather and George Smoot the 2006 Nobel Prize in Physics. COBE was followed by the Wilkinson Microwave Anisotropy Probe, WMAPE, launched in 2001, and the Planck satellite, launched in 2009. These missions mapped the CMB with unprecedented precision, revealing a wealth of information about the universe's age, composition, and evolution. For example, the Planck mission determined that the universe is 13.8 billion years old and consists of about 5% ordinary matter, 26.8% dark matter, and 68.3% dark energy. The CMB also provides insights into the geometry of the universe. According to Einstein's theory of general relativity, the universe's geometry is determined by its total mass-energy content. If the universe has too much matter, it will be closed and eventually collapse in a big crunch. If it has too little matter, it will be open and expand forever. However, observations of the CMB suggest that the universe is flat, meaning its geometry is balanced on the knife edge between these two extremes. This flatness is consistent with the predictions of cosmic inflation and provides further evidence for the existence of dark energy. The CMB and the seeds of structure. The tiny temperature fluctuations in the CMB are not random. They follow a specific pattern that reflects the physics of the early universe. These fluctuations are caused by acoustic oscillations, sound waves that propagated through the hot, dense plasma of the early universe. As the universe expanded and cooled, these sound waves froze in place, imprinting a characteristic pattern on the CMB. This pattern, known as the acoustic peak structure, provides a wealth of information about the early universe. For example, the spacing of the peaks reveals the universe's composition, including the amounts of ordinary matter, dark matter, and dark energy. The height of the peaks provides insights into the density of the early universe and the strength of gravity. By analyzing these features, scientists can test and refine cosmological models, gaining a deeper understanding of the universe's origins and evolution. The CMB also provides evidence for the existence of dark matter. The distribution of temperature fluctuations in the CMB matches the predictions of models that include dark matter, supporting the idea that dark matter played a crucial role in the formation of cosmic structure. Similarly, the CMB provides indirect evidence for dark energy, as the observed flatness of the universe and the rate of cosmic expansion are consistent with the presence of a repulsive force driving the universe apart. The CMB and the future of cosmology. The CMB has revolutionized our understanding of the universe, but it also raises new questions. For example, the precise measurements of the CMB have revealed anomalies that challenge our current understanding of cosmology. One such anomaly is the CMB cold spot, a region of the sky where the temperature of the CMB is significantly lower than expected. Some scientists have speculated that this cold spot could be evidence of a collision with another universe, although this idea remains highly speculative. Another mystery is the Hubble tension, a discrepancy between the rate of cosmic expansion measured from the CMB and the rate measured from nearby galaxies. This tension suggests that our understanding of the universe's composition or the laws of physics may be incomplete. Resolving this discrepancy is one of the most pressing challenges in modern cosmology. Future missions, such as the Simons Observatory and the CMB-S4 project, aim to study the CMB with even greater precision, shedding light on these mysteries and providing new insights into the universe's origins. By combining CMB observations with other cosmological data, such as measurements of galaxy clustering and gravitational lensing, scientists hope to build a more complete picture of the cosmos. The CMB as a window to the past. The CMB is more than just a relic of the Big Bang. It is a time machine that allows us to peer into the universe's infancy. By studying this ancient light, we can learn about the conditions that gave rise to the galaxies, stars, and planets we see today. The CMB also provides a powerful tool for testing our theories of the universe, from the Big Bang and cosmic inflation to dark matter and dark energy. As we continue to explore the CMB, we are reminded of the vastness and complexity of the cosmos. The CMB is a testament to the power of science to uncover the secrets of the universe, revealing the hidden connections between the smallest particles and the largest structures. It is a reminder that, even in the faintest glow of microwave radiation, we can find the echoes of the universe's birth and the seeds of its future. In the next part of our journey, we will explore the future of the universe, from the fate of stars and galaxies to the ultimate destiny of the cosmos. From the smallest particles to the largest structures, the universe is a tapestry of interconnected phenomena, each one telling a part of the story of our cosmic origins. The future of the universe. The universe has been evolving for 13.8 billion years, from the fiery beginnings of the Big Bang to the intricate cosmic web of galaxies, stars, and planets we see today. But what lies ahead? What will the universe look like in a billion years, a trillion years, or even further into the future? The fate of the cosmos is shaped by the interplay of fundamental forces, the behavior of dark matter and dark energy, and the relentless march of time. In this part of our journey, we will explore the possible futures of the universe, from the death of stars to the ultimate fate of all matter and energy. The short-term future, the next billion years. In the relatively near future, on cosmic timescales, the universe will continue to evolve in ways that are familiar to us. Stars will be born, live out their lives, and die, while galaxies will collide and merge, creating new structures in the cosmic web. However, even in this short-term future, there are dramatic changes on the horizon. One of the most significant events in the next billion years will be the collision of the Milky Way and the Andromeda Galaxy. These two galaxies, the largest members of the Local Group, are currently moving toward each other at a speed of about 110 kilometers per second. In approximately 4.5 billion years, they will collide, merging to form a new galaxy, often referred to as Milkomeda. This collision will not be a catastrophic event for the stars within the galaxies, as the vast distances between stars mean that direct collisions are unlikely. However, the gravitational interaction will distort the shapes of both galaxies, triggering bursts of star formation and potentially flinging some stars into intergalactic space. Meanwhile, our own sun will continue its evolution. In about 5 billion years, it will exhaust the hydrogen fuel in its core and begin to expand into a red giant, engulfing the inner planets, including Earth. After shedding its outer layers, the sun will collapse into a white dwarf, a dense, Earth-sized remnant that will slowly cool over trillions of years. This fate awaits most stars in the universe, as they burn through their fuel and end their lives as white dwarfs, neutron stars, or black holes. The medium-term future, the next trillion years. As we look further into the future, the universe will undergo more profound changes. Over the next trillion years, the formation of new stars will gradually decline. Stars are born from clouds of gas and dust, but as galaxies age, their gas reservoirs are depleted, either consumed by star formation or blown away by supernovae and stellar winds. In about 100 billion years, the universe will enter the degenerate era, a time when most stars will have exhausted their fuel and the only sources of light will be the dim glow of white dwarfs, neutron stars, and black holes. During this era, galaxies will continue to evolve. The remnants of stars will slowly sink toward the centers of galaxies, where supermassive black holes reside. These black holes will grow as they consume stars, gas, and even other black holes. Over time, galaxies will become darker and more compact, with their stars and stellar remnants orbiting ever closer to the central black hole. The universe will also continue to expand, driven by the repulsive force of dark energy. As galaxies move farther apart, the cosmic web will stretch and thin, making it increasingly difficult for light from distant galaxies to reach us. In about 150 billion years, all galaxies outside the Local Group will have moved beyond our cosmic horizon, the boundary beyond which light can no longer reach us. The universe will appear increasingly empty, with only the remnants of our own galaxy visible in the night sky. The long-term future, the next 100 trillion years. In the far future, the universe will enter the black hole era, a time when black holes will dominate the cosmos. By this point, all stars will have burned out, and the only sources of energy will be the gravitational interactions of black holes and the faint radiation emitted by their evaporation. Black holes are not eternal. According to Hawking radiation, a process predicted by physicist Stephen Hawking, black holes slowly lose mass and energy by emitting radiation. Over unimaginably long timescales, Even the largest black holes will evaporate. Stellar mass black holes will take about 10^67 years to evaporate, while supermassive black holes could take up to 100 years. As black holes evaporate, they will release their energy into the universe, marking the end of the black hole era. After the last black holes have evaporated, the universe will enter the dark era, a time when all sources of light and energy will have been extinguished. The universe will be a cold, dark, and empty place, filled only with the remnants of matter: electrons, positrons, neutrinos, and photons. The temperature of the universe will approach absolute zero, and all activity will cease. Beyond the observable universe. The universe we can see, the observable universe, is vast, stretching 46.5 billion light-years in every direction. It contains billions of galaxies, each with billions of stars and an intricate web of cosmic structures. But what lies beyond this horizon? Is there more to the universe than what we can observe? The answer to this question takes us to the edge of our understanding, where science meets speculation and where the mysteries of the cosmos deepen. The limits of the observable universe. The observable universe is defined by the distance light has traveled since the Big Bang, approximately 13.8 billion years ago. Because the universe has been expanding during this time, the farthest objects we can see are now about 46.5 billion light-years away. This boundary is not a physical edge, but a limit imposed by the speed of light and the age of the universe. Beyond this horizon, light has not had enough time to reach us, making those regions inaccessible to observation. However, the observable universe is just a tiny fraction of the entire cosmos. According to the theory of cosmic inflation, the universe underwent a period of exponential expansion in the first fraction of a second after the Big Bang. This rapid expansion suggests that the entire universe is much larger, perhaps infinitely larger, than the portion we can see. If this is true, then the observable universe is like a small bubble within an unimaginably vast expanse. The concept of the multiverse. One of the most intriguing ideas in modern cosmology is the multiverse theory, which suggests that our universe is just one of many universes that exist simultaneously. These universes could have different physical laws, constants, and even dimensions, making them radically different from our own. The multiverse concept arises from several theories, including cosmic inflation, string theory, and quantum mechanics. In the inflationary multiverse scenario, different regions of space stop inflating at different times, creating bubble universes that are disconnected from one another. Each bubble could have its own unique properties, such as different values for the fundamental constants of nature. Some bubbles might be hospitable to life, while others might be barren or unstable. String theory, a framework that attempts to unify quantum mechanics and general relativity, also supports the idea of a multiverse. According to string theory, the universe could have additional hidden dimensions, and different configurations of these dimensions could give rise to different universes with distinct physical laws. While the multiverse theory is fascinating, it is also highly speculative. Because these other universes would be beyond our observable horizon, they are, by definition, impossible to detect directly. However, some scientists have proposed indirect methods for testing the multiverse hypothesis, such as looking for evidence of collisions between our universe and other bubbles in the cosmic microwave background, CMB, the shape of the universe. Another question about the universe beyond our horizon is its shape. Is the universe finite or infinite? Is it flat, closed, or open? The shape of the universe is determined by its total mass-energy content and the curvature of space-time. Observations of the CMB suggest that the universe is flat, meaning that parallel lines will never meet and the angles of a triangle add up to 180 degrees. A flat universe is consistent with the predictions of cosmic inflation and implies that the universe could be infinite in extent. However, a flat universe could also be finite if it has a complex topology, such as being shaped like a torus, a donut. If the universe is closed, it would have a positive curvature, like the surface of a sphere. In this case, the universe would be finite, and if you traveled far enough in one direction, you would eventually return to your starting point. A closed universe would eventually stop expanding and collapse in a big crunch. If the universe is open, it would have a negative curvature, like the surface of a saddle. An open universe would be infinite and would continue to expand forever, becoming colder and emptier over time. Current evidence strongly supports a flat universe, but the question of whether it is finite or infinite remains unanswered. If the universe is infinite, then beyond our observable horizon, there could be regions that are identical to ours, containing copies of Earth, the solar system, and even ourselves. This idea, known as the infinite repetition hypothesis, is both mind-bending and humbling. The role of dark energy and cosmic horizons. Dark energy, the mysterious force driving the accelerated expansion of the universe, plays a crucial role in determining what lies beyond our observable horizon. As the universe expands, galaxies are moving farther apart, and the distance to the cosmic horizon is increasing. However, because of the accelerated expansion, some galaxies will eventually move beyond our horizon, making them forever invisible to us. This process creates a cosmic event horizon, similar to the event horizon of a black hole. Beyond this horizon, light from distant objects will never reach us, no matter how long we wait. Over time, the observable universe will shrink, and the night sky will grow darker as galaxies disappear from view. The existence of a cosmic event horizon has profound implications for the future of cosmology. It means that there are regions of the universe that are fundamentally unknowable to us. No matter how advanced our technology becomes, we will never be able to observe or interact with these regions. The possibility of other universes beyond the cosmic horizon. There could be other universes with different physical laws and constants. These universes could be part of a multiverse, a vast collection of universes that exist alongside our own. The multiverse concept is supported by several theories, including cosmic inflation, string theory, and quantum mechanics. In the quantum multiverse scenario, every possible outcome of a quantum event gives rise to a new universe. For example, if you flip a coin, one universe would exist where the coin lands on heads, and another would exist where it lands on tails. This idea, known as the many worlds interpretation, suggests that there are an infinite number of parallel universes, each representing a different outcome of every possible event. While the multiverse theory is intriguing, it is also highly speculative. Because these other universes would be beyond our observable horizon, they are, by definition, impossible to detect directly. However, some scientists have proposed indirect methods for testing the multiverse hypothesis, such as looking for evidence of collisions between our universe and other bubbles in the cosmic microwave background, CMB. The philosophical implications. The idea of a universe, or multiverse, beyond our observable horizon raises profound philosophical questions. What does it mean for our understanding of reality if there are regions of the cosmos that are forever hidden from us? How do we reconcile the vastness of the universe with our limited ability to observe and comprehend it? These questions remind us of the humility and wonder that come with studying the cosmos. The universe is far more complex and mysterious than we can imagine, and our knowledge is limited by the boundaries of our observations and the laws of physics. Yet, even within these limits, we have made remarkable progress in understanding the origins, evolution, and structure of the universe. The search for answers, the quest to understand what lies beyond the observable universe, is one of the most exciting and challenging endeavors in modern science. It requires us to push the boundaries of our knowledge, to develop new theories and technologies, and to explore the deepest mysteries of the cosmos. Future missions, such as the James Webb Space Telescope and the Euclid Space Telescope, will provide new insights into the early universe and the nature of dark energy. Advances in theoretical physics, such as string theory and quantum gravity, may offer new perspectives on the structure and origins of the cosmos. As we continue to explore the universe, we are reminded of the vastness and complexity of the cosmos. The observable universe is just the beginning of our journey, and beyond it lies a realm of infinite possibilities, waiting to be discovered. In the next part of our journey, we will explore the mysteries of black holes, from their formation and properties to their role in shaping the universe. From the smallest particles to the largest structures, the universe is a tapestry of interconnected phenomena, each one telling a part of the story of our cosmic origins. The role of black holes and quantum gravity. Black holes are among the most mysterious and fascinating objects in the universe. They are regions of space where gravity is so strong that nothing, not even light, can escape. Born from the collapse of massive stars or the merging of smaller black holes, these cosmic giants play a crucial role in shaping the universe. But black holes are more than just gravitational traps. They are also windows into the deepest mysteries of physics, where the laws of quantum mechanics and general relativity collide. In this part of our journey, we will explore the nature of black holes, their role in the cosmos, and the quest to unify quantum mechanics and gravity. The formation and properties of black holes. Black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity. For a star with a mass more than about 20 times that of the Sun, the core collapse is so violent that it creates a singularity, a point of infinite density and zero volume. Surrounding the singularity is the event horizon, the boundary beyond which nothing can escape the black hole's gravitational pull. Black holes come in different sizes, from stellar mass black holes, which are a few times more massive than the Sun, to supermassive black holes, which can have masses billions of times greater than the Sun. Supermassive black holes are found at the centers of most galaxies, including our own Milky Way. They play a crucial role in the evolution of galaxies, influencing the motion of stars and gas, and powering some of the most energetic phenomena in the universe, such as quasars and active galactic nuclei. Black holes as cosmic laboratories. Black holes are not just destructive forces, they are also cosmic laboratories where the laws of physics are pushed to their limits. Near the event horizon, the gravitational field is so strong that it warps space and time, creating effects predicted by Einstein's theory of general relativity. For example, time slows down near a black hole, a phenomenon known as time dilation. If you were to observe someone falling into a black hole, they would appear to slow down and freeze at the event horizon, never quite crossing it from your perspective. Black holes also provide a unique environment for testing the interplay between quantum mechanics and gravity. According to quantum mechanics, empty space is not truly empty, but is filled with virtual particles that constantly pop in and out of existence. Near the event horizon of a black hole, these virtual particles can be separated, with one particle falling into the black hole and the other escaping as Hawking radiation. This process, predicted by physicist Stephen Hawking in 1974, causes black holes to slowly lose mass and energy over time, eventually evaporating. Hawking radiation is one of the few known phenomena that bridges the gap between quantum mechanics and general relativity. However, it also raises profound questions about the nature of information in the universe. According to quantum mechanics, information cannot be destroyed, but if a black hole evaporates completely, what happens to the information about the matter that fell into it? This problem, known as the black hole information paradox, remains one of the greatest unsolved mysteries in physics. The search for quantum gravity. The study of black holes highlights the need for a theory of quantum gravity, a framework that unifies quantum mechanics and general relativity. Quantum mechanics describes the behavior of particles on the smallest scales, while general relativity describes the behavior of gravity on the largest scales. However, these two theories are fundamentally incompatible, and their unification is one of the most important goals in modern physics. One promising approach to quantum gravity is string theory, which proposes that the fundamental building blocks of the universe are not particles but tiny, one-dimensional strings. These strings vibrate at different frequencies, giving rise to the particles and forces we observe. String theory also predicts the existence of extra dimensions, which could help explain the nature of gravity and the behavior of black holes. Another approach is loop quantum gravity, LQG, which suggests that space itself is made up of tiny, discrete loops. In LQG, the fabric of spacetime is not smooth but granular, with a minimum length scale known as the Planck length. This granularity could prevent the formation of singularities, offering a way to avoid the infinite densities predicted by general relativity. Both string theory and loop quantum gravity offer potential solutions to the black hole information paradox and other mysteries of the cosmos. However, they are still in the early stages of development, and much work remains to be done to test their predictions and reconcile them with observations. Black holes and the structure of the universe. Black holes play a crucial role in the evolution of the universe. Supermassive black holes, in particular, are thought to influence the formation and growth of galaxies. When matter falls into a supermassive black hole, it releases enormous amounts of energy, powering quasars and active galactic nuclei. These energetic phenomena can heat and ionize the surrounding gas, preventing it from collapsing to form new stars and shaping the structure of galaxies. Black holes also play a role in the cosmic web, the large-scale structure of the universe. The gravitational pull of black holes can attract and concentrate matter, creating the dense regions where galaxies and galaxy clusters form. At the same time, the energy released by black holes can push gas and dust away, creating the voids that separate the filaments of the cosmic web. The future of black hole research. The study of black holes is entering a new era, thanks to advances in observational technology and theoretical physics. In 2019, the Event Horizon Telescope, EHT, captured the first image of a black hole, revealing the shadow of the supermassive black hole at the center of the galaxy M87. This groundbreaking achievement provided direct evidence of black holes and opened new avenues for studying their properties. Future missions, such as the Laser Interferometer Space Antenna, LISA, will detect gravitational waves from merging supermassive black holes, providing new insights into their formation and evolution. At the same time, advances in quantum gravity research could shed light on the nature of black holes and the fundamental laws of physics. The philosophical implications of black holes. Black holes are more than just physical objects. They are also symbols of the limits of human knowledge. They challenge our understanding of space, time, and reality, forcing us to confront the deepest questions about the nature of the universe. What happens inside a black hole? Is information truly lost, or is it somehow preserved? Can we ever unify quantum mechanics and gravity? These questions remind us of the humility and wonder that come with studying the cosmos. The universe is far more complex and mysterious than we can imagine, and our knowledge is limited by the boundaries of our observations and the laws of physics. Yet, even within these limits, we have made remarkable progress in understanding the origins, evolution, and structure of the universe. In the next part of our journey, we will explore the mysteries of dark matter and dark energy, the invisible forces that shape the universe on the largest scales. From the smallest particles to the largest structures, the universe is a tapestry of interconnected phenomena, each one telling a part of the story of our cosmic origins. Philosophical implications. The study of the universe is not just a scientific endeavor, it is also a deeply philosophical one. As we explore the cosmos, from the smallest particles to the largest structures, we are confronted with profound questions about the nature of reality, our place in the universe, and the limits of human knowledge. These questions challenge us to think beyond the boundaries of science and to consider the broader implications of our discoveries. In this final part of our journey, we will explore the philosophical implications of cosmology, from the nature of time and existence to the meaning of life in a vast and seemingly indifferent universe. The nature of reality. One of the most fundamental questions in philosophy is the nature of reality. What is the universe made of? Is it fundamentally physical, or are there aspects of reality that transcend the material world? Cosmology provides some answers to these questions, but it also raises new ones. For example, the discovery of dark matter and dark energy has revealed that most of the universe is made up of substances that we cannot see or directly detect. These mysterious components challenge our understanding of matter and energy, suggesting that the universe is far more complex than we once thought. At the same time, theories like string theory and quantum gravity propose that the fabric of reality may be woven from tiny strings or discrete loops, hinting at a deeper, hidden structure beneath the surface of the observable world. These discoveries remind us that reality is not always what it seems. The universe is full of mysteries that defy our intuition and challenge our understanding. As we continue to explore the cosmos, we are forced to confront the limits of our knowledge and to consider the possibility that there are aspects of reality that are beyond our comprehension. The nature of time. Time is one of the most enigmatic aspects of the universe. We experience time as a linear progression, moving from the past to the future, but the laws of physics suggest that time may be more complex than our everyday experience suggests. According to Einstein's theory of general relativity, time is not absolute, but is intertwined with space in a four-dimensional fabric known as spacetime. This fabric can be warped by gravity, causing time to slow down or speed up depending on the strength of the gravitational field. Near a black hole, for example, time slows down dramatically, a phenomenon known as time dilation. At the same time, the arrow of time, the direction in which time flows, remains one of the great mysteries of physics. Why does time move forward and not backward? The second law of thermodynamics, which states that entropy, or disorder, always increases, provides a partial explanation, but it does not fully account for the asymmetry of time. The study of cosmology also raises questions about the beginning and end of time. The Big Bang is often described as the beginning of time, but what does that mean? Was there a before the Big Bang, or is time itself a product of the universe's creation? Similarly, the ultimate fate of the universe, whether it ends in a big freeze, a big rip, or a big crunch, has profound implications for our understanding of time and existence. The meaning of life in a vast universe. The universe is vast, ancient, and seemingly indifferent to human existence. In the face of this cosmic scale, it is natural to wonder about the meaning of life. Are we alone in the universe, or is life a common phenomenon? Does our existence have a purpose, or are we merely the product of random chance? The search for extraterrestrial life is one of the most exciting areas of modern science. Missions to Mars, the exploration of Europa and Enceladus, moons of Jupiter and Saturn, and the study of exoplanets in the habitable zones of distant stars are all part of the effort to find signs of life beyond Earth. The discovery of even microbial life elsewhere in the universe would have profound implications for our understanding of biology and our place in the cosmos. At the same time, the anthropic principle suggests that the universe is finely tuned for the existence of life. The fundamental constants of nature, such as the strength of gravity and the charge of the electron, are precisely balanced to allow the formation of stars, planets, and life. Some scientists and philosophers argue that this fine-tuning is evidence of a deeper purpose or design, while others see it as the result of a multiverse, where different universes have different constants and only those suitable for life give rise to observers. The limits of human knowledge. The study of the universe also raises questions about the limits of human knowledge. Are there aspects of reality that are fundamentally unknowable? The cosmic horizon, the boundary beyond which light has not had time to reach us, suggests that there are regions of the universe that are forever hidden from our view. Similarly, the nature of dark matter and dark energy may be beyond our current understanding, requiring new theories and technologies to unravel. The black hole information paradox is another example of the limits of our knowledge. According to quantum mechanics, information cannot be destroyed, but if a black hole evaporates completely, what happens to the information about the matter that fell into it? This paradox challenges our understanding of the fundamental laws of physics and suggests that there may be aspects of reality that are beyond our current theories. The role of science and philosophy. The study of the universe is a collaborative effort between science and philosophy. Science provides the tools and methods for exploring the cosmos, while philosophy helps us to interpret the meaning and implications of our discoveries. Together, they offer a deeper understanding of the universe and our place within it. As we continue to explore the cosmos, we are reminded of the humility and wonder that come with studying the universe. The universe is vast, complex, and full of mysteries that defy our intuition and challenge our understanding. Yet, even within these limits, we have made remarkable progress in understanding the origins, evolution, and structure of the universe. The beauty of the cosmos. Finally, the study of the universe reminds us of the beauty and wonder of the cosmos. From the intricate patterns of the cosmic web to the violent collisions of black holes, the universe is a tapestry of interconnected phenomena, each one telling a part of the story of our cosmic origins. The night sky, with its countless stars and galaxies, is a source of inspiration and awe, reminding us of the vastness and complexity of the cosmos. As we look to the future, we are filled with a sense of curiosity and determination. The universe is full of mysteries waiting to be uncovered, and the quest for knowledge is a journey that will continue for generations to come. Whether we are exploring the nature of black holes, the origins of the universe, or the meaning of life, we are part of a grand adventure that transcends time and space. In the end, the study of the universe is not just about answering questions, it is about asking them. It is about pushing the boundaries of our knowledge, challenging our assumptions, and exploring the unknown. It is about finding beauty in the cosmos and meaning in our existence. And it is about reminding ourselves that, in the vastness of the universe, we are all connected, part of a grand cosmic story that is still being written. As we reach the end of our cosmic journey, we are left with more questions than answers. And perhaps that is the most beautiful part of exploring the universe. From the fiery birth of the Big Bang to the enigmatic depths of black holes, from the invisible grip of dark matter to the relentless push of dark energy, the cosmos is a tapestry of mysteries that both humbles and inspires us. The universe does not yield its secrets easily. It challenges us to think beyond the limits of our understanding, to question the nature of reality, time, and existence itself. Yet, in this vast and seemingly indifferent cosmos, we find a profound connection, a reminder that we are made of the same stardust that lights up the night sky. Our curiosity, our drive to explore, and our quest for meaning are what make us uniquely human. As we gaze into the infinite expanse, we realize that the universe is not just out there, it is within us. Every discovery, every unanswered question, and every moment of wonder brings us closer to understanding not only the cosmos, but also ourselves. The journey is far from over. In fact, it has only just begun. So let us continue to look up, to dream, and to explore, for the universe is not just a place, it is a story, and we are all part of its unfolding narrative. The stars may be distant, but the quest to understand them is what brings us together, here and now, under the same infinite sky.